All right. So here we go. Section 5.6. And I did post this on Canvas. This PowerPoint. Was anybody able, because one person said they were not able to print this out properly or something. I had to email it to them specifically, but was anybody successful in opening this up from our Canvas website? And maybe downloading it or anything? Anybody else do this? Or all right, well, I'm assuming it's the file's okay, and you may have to download the file now, ladies and gentlemen. So, for instance, let me show you what I'm talking about. When you go to our Canvas site here, hold on a second here. Where are we? Okay, when you go to our Canvas site here, when you click on lecture notes and click on like 5.6 PowerPoint down at the bottom here. Now, it may not render it properly in this window, and if it doesn't, just click on this hyperlink here. This blue hyperlink says download section 5.6 PowerPoint, and it will download it, and then you can open it up once it downloads it using your PowerPoint application on your computer, and it should render it then properly. You have to click on enable editing. All right. So it may not always render it properly in Canvas, but it will render it properly when you download and open it up using PowerPoint. All right, so let's begin here. Exponents and scientific notation. When we get done, we'll be able to define integer exponents, use rules for exponents, and there's quite a few, convert between scientific and decimal notation, perform operations with numbers in scientific notation, and use scientific notation in applied problems. All right, so here we go with exponents. We read this notation as a raised to the nth power. And what that means is, I'll tell you what it doesn't mean. It doesn't mean to take a and multiply it by n. That's not what it's saying. This exponent n, this little n is called the exponent up here. It's saying, it's telling us or instructing us how many times to multiply the base a by itself. So a raised to the nth power means a gets multiplied by itself n times. All right, exponents are a very efficient way of representing repeated multiplications. For example, 5 times itself 4 times can be written more compactly as 5 raised to the 4th power. All right, and again, the little 4 is called the exponent. That instructs us how many times 5 gets multiplied by itself. You never multiply the base by the exponent. So this is not 5 times 4. It's saying 5 times itself 4 times. Which, if you were to evaluate that, you would get 5 times 5 is 25, times 5 is 125, times 5 is 625. Okay, so 5 to the 4th power is 625. So in general, a with the little n up here is read as a raised to the nth power. Now, when the exponent is 2, such as like 5 raised to the 2nd power, we normally say that the base is being squared. So we would read this as 5 squared, which means 5 times 5. When the exponent is 1, normally we don't indicate it, or we don't write it explicitly. So a to the 1st power, or a raised to the 1st power, is equal to as if we just say a. To say a is to imply that the exponent on a is 1. Now, there do exist negative exponents, ladies and gentlemen, not just positive exponents. And here is the definition of negative exponent. If I have a raised to the negative n power, that suggests that we are to take the reciprocal of the base a. So base a then would get flipped down into the denominator. So you can think of this a to the negative n power as being over 1. And to change the sign on the exponent from negative to positive, the price we pay is we have to reciprocate a down into the denominator. And so we would have 1 over a to the n power. Now, As odd as it may seem, any quantity raised to the 0th power by definition of mathematics is equal to 1. All right, that's always true. All right, here's some examples. They want us to evaluate these 6 raised to the 3rd power. And ladies and gentlemen, when the exponent is 3, as it is on 6 here, we usually say that the base is being cubed. So we would read this as 6 cubed. 6 cubed. Remember, if the base is 2, we say the base is being squared. So what does it mean to cube 6? It means we need to multiply 6 by itself 3 times. And that would evaluate to 216. All right, the next one has a negative exponent. We have 3 raised to the negative 4 exponent. And before we can evaluate this expression, which is a negative exponent, we always have to change the sign on the exponent and make sure the exponent's a positive. To do that, we're going to have to tap into the definition of negative exponent, and we're going to have to reciprocate or flip this base of 3 down into the denominator, in which case 3 to the negative 4 power is equivalent to 1 over 3 to the positive 4th power. That means it's going to be 1 over 3 times 3 times 3 times 3, which is 1 over 81. Finally, 9 raised to the 0th power is going to be equal to 1. Anytime we raise anything to the 0th power, it's equal to 1. Any questions about that there? All right, rules for exponents. There's quite a few rules, ladies and gentlemen, and it ultimately just comes down to memorizing these rules. For any non-zero real numbers a and any integers m and n, so m and n have to be integers like -2 or -1 or 1 or 2 or 3. Okay, we're not into these exponents being fractions yet, although they do exist. We're going to assume for now that our exponents are always integers. All right. The product rule says this: if I have a raised to the nth power, multiplying that by a raised to the nth power, this first rule of exponents indicates that we are to keep the base the same, a, and we are to add the exponents. So a to the mth power times a to the nth power is a to the m plus n power. Okay, so a to the mth power times a to the nth power is a to the m plus n power. So when you multiply like bases, you keep the base the same and add exponents. All right. Now, the quotient rule says that when we divide like bases, our bases are both a here. When we divide like bases, we are to always subtract, keep the base the same and subtract the exponents. Notice specifically the order of subtraction. A to the mth power divided by a to the nth power is a to the numerator power m, subtract the denominator power n. Notice the order of subtraction, very important there. Okay, and this a to the m over m minus n power is understood to be over 1. Understood. All right, so 2 rules. When we multiply like bases, keep the base the same and add the exponents. When we divide like bases, keep the base the same and raise it to the difference between the exponents. Another property of exponents. When we raise a power to a power, when we have like a to the mth power raised to the nth power, this is not equal to a to the m raised to the nth power. No, what we are to do is keep the base the same and multiply the exponents. So this is equal to a to the m times n power. So when you raise a power to a power, you multiply exponents. So we've seen 3 rules so far. All right. Okay, now let's see if we can simplify these expressions. So ladies and gentlemen, I'm going to call this classwork number 1. Let's see if you can do these here. Classwork 1. I want you to evaluate each one of these expressions here, okay? Or they say simplifying. All right. So go ahead and see if you can tap into these rules. Remember, we've seen 3 rules so far. We've seen when you multiply like bases, you add exponents. When you divide like bases, you subtract exponents. And when you raise a power to a power, you multiply the exponents. All right, so see if you can maybe do those problems there. All right, so 3 raised to the 3rd power times 3 to the 5th power. We're going to keep the base 3 the same. And what do we do with our exponents? Anybody?
You add them.
Add the exponents. So you know what this is going to be equal to? It's going to be equal to 3 raised to the 8th power. Now, that's kind of a big number, and you know, you can use a calculator. Depending on what machine you use, well, let's see here. Okay. So, ladies and gentlemen, on the TI-30, you would raise 3 to the 8th power this way. You type in 3, you'd hit your general power button. This is called your general power button. 3 raised to the 8th power, and then you would hit your enter button or equal button, and you would get what? That's going to be a big number, as you would expect. And let's see, what does that give us? 3 raised to the 8th power there. That's a pretty big number there. I'm getting 6,561. So 6,561 is, are you able to use your power button on your calculator to take care of that business there? Now, some calculators have, it depends what calculator you're using. Some calculators have this for a power button. They have like X raised to like the Y power. Maybe that's your power button. Okay. And maybe some calculators have maybe this for their power button, X to the nth power. And then you type in 8. Okay, whatever. Any one of those will give you the same result. So just make sure if you do have a calculator that you're able to raise 3 to the 8th power. Make sure you're able to do that. I'm assuming everybody is able to do that one way or another. Is that correct? On a scientific calculator?
Yes.
Yes.
Yeah, just make sure you know how to use the machine a little bit. Okay, here we go. 5 to the 4th power divided by 5 to the 6th power. We're dividing like bases, and so what we do according to the rule we've seen is we keep the base the same, and we are to subtract the exponents, specifically the numerator exponent minus the denominator exponent. Notice in that order. So this is going to be, now 4 minus 6 is -2, so this is going to be 5 raised to the -2 power. And we cannot evaluate this until we make the exponent become a positive. Don't try to evaluate this unless you have a positive exponent. Now this is understood to be over 1. So using the definition of negative exponent, now the 5 gets flipped down into the denominator, in which case we'll have our equivalent expression as being 1 over 5 raised to the +2 power. Now we can take care of business, because 5 squared, or 5 to the second power, is saying 5 times 5. Not 5 times 2, but 5 times 5. And therefore we have 1 over 25 as being the final result, or the simplification of that that problem there. Okay. Finally, anybody get that for B?
I got it, but I didn't put it as a fraction, but I got that answer.
Okay.
Yeah, I got it too. I just did the 5 to the -2 power right away, and I
On the
just
calculator?
yeah.
Okay. Yeah. Now, if you do that, you're going to get the decimal approximation of 1 over 25, which actually is exactly equal to 0.04. Did you get 0.04? Well, so if you raise 5 to the -2 power on a calculator, this is what it's going to report. Well, you know what? How do you read this decimal? Isn't that 4 hundredths? 4 over 100? 4 hundredths? But doesn't 4 over 100 reduce down to what? What does that reduce down to? That reduces down to 1 over what? 25, doesn't it? You see that there?
Yeah.
It's the same thing. All right, finally, C, raising a power to a power, 2 to the third power, raised to the fourth power. The property says we keep the base the same, and we are to multiply the exponents. So this is 2 raised to the 3 times 4 power, which is saying 2 raised to the 12th power, which means 2 times itself 12 times. So 2 times 2 times 2 times 2 times itself 12 times. A lot easier to take care of this business on your calculator. Raise 2 to the 12th power, and you're going to get a sizable number, which is a what? 4,096. Anybody get that? 4,096. Can we get that?
So with these would be the only time that you wouldn't do the order.
Well, the order of operations says we do exponents after we do parentheses. So, I mean, okay, I see what you're saying. You know, technically, another way you could have done this problem, instead of, you know, raising 2 to the product of the exponents, is you could have done strictly what's inside the parentheses, and 2 to the third power is 2 times 2 times 2, which is what, 8?
Mhm.
And then you could raise 8 to the fourth power. Okay, so that's another way to do the problem. You would get 4,096 also.
Yeah,
So,
that's the way I did it. Okay.
yeah, whether you do it, you know, using the rule of exponents and multiplying the exponents, or just, you know, abide by the order of operations, yeah, you should get 4,096 either way. Okay, so and this is just going over what I just indicated lays on. All right, now scientific notation. Scientific notation, like I said, is a nice way of representing extremely large or extremely small numbers. Scientific notation has a very strict format, though. So we really need to memorize this format requirement. It says a number is in scientific notation when it's written as a decimal with one non-zero digit to the left of the decimal point times some power of 10. This is useful when working with really large or small numbers. Expressing numbers in terms of powers of 10 allows us to write a lot of digits with just a few symbols. All right, I'm going to expound upon this here. I want to show you the strict format for scientific notation, because we're not really doing that in the PowerPoint here. All right, this is the strict form for scientific notation. A point, okay, times 10 raised to the nth power. Now this number A here has to come from this list. This number A either has to be a 1 or it has to be a 2 or a 3 or a 4 or a 5 or a 6 or a 7 or an 8 or a 9. There you go. So this A cannot be 10, okay? It cannot be anything larger than a 9. So it either has to be the integer 1, 2, 3, 4, 5, 6, 7, 8, or 9. And notice the decimal point is just to the right of that integer. This is called scientific notation format, all right? N is the exponent, and the exponent is going to be an integer. So it could be positive or negative. In fact, I'll let you in on a little secret here. When our exponent is positive, we are talking about large numbers. When our exponent is negative, we're talking about small numbers. All right, that's the way it works there. Okay. All right, so that is strict scientific notation format. All right, now, how do we write a number in scientific notation form? Well, step number 1, we move the decimal point either to the right or left so that there is exactly one non-zero integer digit to the left of the decimal point. Okay, and again, that non-zero integer digit has to be a 1, a 2, a 3, a 4, 5, 6, or 7, or 8, or 9. Step 2, write the resulting number times 10 to some appropriate power, which will be determined by the number of places you had to move your decimal point to place it in the right spot according to step 1. If the decimal point was moved to the left, then the exponent on 10 is going to be it's going to be a negative exponent, and that will be the exponent which will be equivalent to the number of places you moved the decimal point to the left. If the decimal point was moved to the right, the exponent on 10 is going to be a positive. Wait a minute here. Let me backtrack what I said. Ladies and gentlemen, if you move the decimal point to the left, the exponent on 10 is going to be a positive. Okay, and it's going to be equal to the number of places you had to move your decimal point so that step 1 is satisfied. If you move your decimal point to the right so that step 1 is satisfied, then your exponent on 10 is going to be negative. Okay, and it will be the negative number of places that you had to move your decimal point. All right, this is about as clear as mud so far in our minds. It's only going to come into existence with examples. All right, here we go. We're going to try to write each of these numbers in scientific notation form. All right, ladies and gentlemen, the first number here, A, is that a large number or a small number?
Large number.
A very large number, correct? So where is the decimal point understood to be presently for this large number? I don't see a decimal point. I see commas, but forget about the commas. Where's the decimal point of this large number?
It should be at the very end of it.
That's right. It's just to the right of the ones digit, which is this last 0 here. That's in the ones place. We have to, in order to get our number from, they call this decimal notation form, or sometimes they call it standard form, to get it into scientific notation form, we have to move our decimal point so that the digit to the left of the decimal point is either a 1, a 2, a 3, 4, 5, 6, 7, 8, or 9. So where would I move my decimal point? Would I move it right here? No good, because to the left of the decimal point would be the number 357. That's not in the list of integers I cited. Would I move it between the 5 and the 7? No good, because to the left of the decimal point is the number 35. That's not in the list of 1 to 9 that I indicated. Would I move it to the left of 3? No good, because the left of 3 is understood to be the digit 0, and 0 is not in the list that I mentioned. Ladies and gentlemen, where's the only place that the decimal point could go in order for our non-zero digit to the left of the decimal point to be either a 1, 2, 3, 4, 5, 6, 7, 8, or 9?
The 2.
Wait a minute. You would move the decimal point where?
To the right of the 2.
To the right of the 2. Now, if we move it to the right of the 2, unfortunately, the number that is to the left of our decimal point would be 3,572. And that number is not in the list of, required integers that I indicated, 1, 2, 3, 4, 5, 6, 7, 8, or 9.
Move it to the right of the 3.
Okay, here we go. But there's only one place that decimal point can go for this to be in scientific notation form. It has to go between the 3 and the 5, because to the left of the decimal point would be the integer 3, and 3 is in that list of, that I indicated. And remember again, what was our list? Our list says the non-zero digit to the left of the decimal point has to be either a 1, a 2, a 3, a 4, a 5, 6, 7, 8, or 9. So yeah, to put it in scientific notation form, we have no choice, but that decimal point has to go between the 3 and the 5. Now, how many places must we move it to get it there? Here we go. 1, 2, 3, 4, 5, 6, 7, 8. What? 9 places? Son of a gun. Hold on a second. We got to move it 9 places, correct? 6, 7, 8, 9 places. All right, so here's how we write this number in scientific notation form. We say now it is 3.572 times 10 to 10 raised to the what power? And will the exponent on 10 be positive or negative? Is this a large or small number?
Large.
A lot larger than 1, isn't it? So this will be a positive what? How many places did I move it again?
9.
Be raised to the 9th power, positive 9th power. That number is now in scientific notation form. So 3.52 times 10 to the 9th power means this number, which would be 3,572,000,000, correct? Everybody see that there, how we got in scientific notation form?
You
Why-
forgot
why
your
do we have-
7 there with the 3.57.
Oh, whoa. Yeah, I'm missing, forgot the 7.
Yeah.
Yeah, sorry about that. It would be 3.572 times 10 to the 9th power. There we go. All right. Do we understand how we put this in scientific notation form? All right. Now help me out with this next number. Is this a big or a small number here? This next one.
Small number.
Little one.
Very, very small number. Here's 1 whole. Do you agree? That's the ones place. This isn't even close to being 1 whole. So this is definitely a small number. So where would I have to move my decimal point so that it's in strict scientific notation format?
To the left.
Well, if we move it to the left, we're going to have nothing but zeros to the left of our decimal point.
I
And
meant right.
it can't be a 0. It's got to be a 1,
Between
2,
the-
3, 4, 5, 6, 7, 8, or 9. Where's that?
Between the 8 and the 7.
Yeah, the only place we can put that decimal point for this to be in strict scientific notation form is between the 8 and the 7, because to the left of the decimal point then would be the integer 8. And 8 is in that list that I cited. How many places to get it there? 1, 2, 3, 4, 5 places. So in scientific notation form, this is going to be 8.7 times 10 to the what power? Positive or negative 5 power? Is this a large or small number?
It's a small number, so it's
Very
negative.
small number. So the exponent's negative. And there you go. 8.7 times 10 to the negative 5th power is equivalent to this very small number. Let's see if we can read this number. Tens, hundreds, thousands, 10,000s, 100,000s, millions. You know how we would read this number? We would say 87 millions. 87 millions. This is only 87 millions of 1 whole. It's not even close to being close to 1 whole. That's an extremely small number. All right, any questions how we got these numbers in scientific notation form? Okay. All right, and then they're just indicating what the results should be there. Okay. There you go. All right. Now, rules for converting a number in scientific notation form back to decimal notation form. Suppose you want to go backwards. If I give you a number in scientific notation form, can you put it back in standard form or decimal notation form? A, if the exponent of the power of 10 is positive, think about it, ladies and gentlemen, if the exponent's positive on 10, would I move my decimal point to the right or to the left to put the number back in decimal notation? If the exponent's positive on 10, we're talking about a very large number, correct? So where would we move our decimal point? Think about it, right or left?
left.
Well, if you move it to the left, then your decimal notation form for the number is gonna be a small number. You'd have to move it to the what? To the right, okay? To establish a large number. Now, if your exponent on 10 is negative, we're talking about a small number now. We're talking about a number less than 1. So now you'd have to move your decimal point to the left, okay, to write your number in decimal notation form. All right, like I said, with examples, this will start to come to life because right now it's just a bunch of words. All right, here we go. Suppose I give you these two numbers in scientific notation form, and I want you to write them back in equivalent decimal notation form. Is the first number a large or small number?
Large.
It's a large number. So therefore, okay, think about it. If I move my decimal point to the left, is my number getting larger or smaller if I move it to the left?
Smaller.
It's getting smaller and smaller and smaller. We don't go to the left. This is a big number. This number is supposed to be larger than 1. So in this case, we're going to move our decimal point 8 places to the right. So we got to go 8 places to the right. So here we go. The decimal point's originally right here. So 1, 2, 3, 4. I got to add a 0. 5. I got to add another 0. 6. I got to add another 0. 7. Add another 0. And then finally 8. Add another 0. The decimal point would be way at the end here. You see that there? 8 places to the right. And how would we read that number? How would we read this number here? You know, they put commas in here, so it makes our life easier in reading the number. But be very careful when you're working with decimals. Commas can be misinterpreted as a decimal point if you're not careful or if you're a little sloppy. All right. I will put commas in here so that we can read this more conveniently. How would we read this number? It's a big old number.
419,200,000.
That's right, 419,200,000. There you go. And if we had this amount of money in our bank account, would we be here right now doing this?
Mhm.
Well, you never know. We might be bored with life. Do you agree? Never say never.
Not
Yeah.
a chance.
Not a chance, huh? I'll take boredom any day, right? Okay, anyways, ladies and gentlemen, be careful with the commas because like I said, commas can look like decimals. If you're sloppy with the commas, you know, if you don't really draw a comma correctly, it can look like a decimal point. Be careful with those. All right, that's why I really don't like commas in numbers because they really can be confused with decimal points. Now, this next number, small or large? This next number, small or large? This is a very small number, correct? So think about it. Am I going to go 8 places to the right? If I go 8 places to the right, this number is going to get what? Bigger and bigger and bigger. Do you agree?
I think I go to the left.
Yeah, we don't go to the right. We go to the left. This is a small number. This is number supposed to be less than 1. So we got to go 8 places to the left. So here we go. I'm going to put my 637 over here. And then I'm going to go 8 places to the left with this point. Here we go. 1, 2, got to add a 0. 3, got to add a 0. 4, another 0. 5, another 0. 6, another 0. 7, another 0. And then 8 places. Finally, our decimal point would go right there. Okay, so that's a very, 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 very small number. And whether you put a 0 in front of the decimal point, that's up to you. That's optional. I think nurses always put a decimal point, a 0 before the decimal point for small numbers to avoid possible confusion. For instance, ladies and gentlemen, if you're a nurse and let's say you had a hard night of partying and you came in really groggy and tired, and you're not paying attention to business here, you agree you could maybe misread this as 5 milligrams of some medication? Okay, to avoid that possible ambiguity or big mistake, nurses are taught to put a 0 before the decimal point because it throws up a flag and says, wait a minute, there's a decimal point here. So that should be 5/10 of a milligram. Do you agree there's a huge difference between 5 milligrams and 5/10 of 1 milligram? There's a big difference here. That's a humongous difference, ladies and gentlemen. So we got to be very careful. All right. So yeah, decimal points need to really be paid attention to. All right, so this is a small number, and I don't know, anybody think they can read this decimal for us? That's a challenging question. How would you read this decimal? 637 what? The 7 sits in what place way out here? Let's see, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions. So how would we read this? 637 what? 10 billions. Do you agree? 637 10 billions of one whole. This number is not even close to being close to being close to being close to one whole. That's an extremely small number. All right, so are we understanding how to go back and forth between scientific notation form and decimal notation form? Back and forth between the two different forms here. All right. Now, check this out. Suppose we're asked to multiply 20 million by 42 what billion? Do you agree? There's going to be a lot of zeros in that product. Now, in decimal form, this is obviously a challenging, task. But ladies and gentlemen, if we convert these numbers into scientific notation form, our life is actually rendered trivially easy. Okay, so instead of taking 20 million and multiplying it by 42 billion, which is going to be a nasty little problem with all the zeros, why not write them both in scientific notation form? 20 million would be written as 2 times 10 to the 7th power, with the understanding that the decimal point is just to the right of the 2. Okay, and 42 billion would be written as 4.2 times 10 to the 10th power. Now, when you multiply these scientific notation numbers together, we multiply the 2 and the 4.2 together, and then we multiply the like bases of 10 together. Well, ladies and gentlemen, when we multiply like bases together, we what? Add the exponents. So 10 to the 7th power times 10 to the 10th power is 10 to the 7 plus 10 power, or 10 to the 17th power here. And 2 times 4.2 is 8.4. There's your answer. It's 8.4 times 10 to the 17th power when you multiply 20 million by 42 billion. And how would I put this in scientific notation form? Just curious. How would I move my decimal point, to the right or left? $17 places to the right or left? What do you think?
Right.
To the right. That's a huge number. So we got 8. Okay, and then you got to move decimal 1 place to the right of the 4. That's 1 place. But then we got to move it 16 more places to the right, which means I have to add how many zeros?
7.
16, because I already moved the decimal point 1 place to the right of the 4, correct? That uses 1 place up, but I got 16 more places, don't I? 16 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then the decimal point goes at the end. That's what that number would be in, decimal format or decimal notation. That's a huge number. Gosh, how would we even read such a number there? Is that even possible? Let's see. Challenging question, isn't it? How would you read this number as a number here? Well, let's see. We got a lot of zeros here. Maybe I could put some commas in here. Comma, 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 comma. Now that's how many zeros? 3, 6, 9, 12. Okay. So, ladies and gentlemen, are you ready for this? I would read this number as 840,000 trillion. 840,000 trillion. There's the ones placed, the tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, trillion, 10 trillion, 100 trillion. And then after trillion, it's just a very big number. Do you agree? So I would read it as 840,000 what? Trillion. Trillion has 12 zeros. 3, 6, 9, 12. We all see that? 840,000 trillion. That's how you would read that number. That's a big number. Does anybody have 840,000 trillion dollars on this planet?
I wish.
No,
Not
well,
yet.
maybe our federal debt is getting there. Do you agree? But yeah, I don't think there's any 840,000 trillionaires out there yet. Hopefully it's one of you soon, but we'll see. Hey, wasn't that lotto up to $1 billion or something? Did that go last night? Did they do it last night or was it tonight? Or I can't remember. I don't play. But does anybody remember? I think it was what, up to $1 billion, wasn't it? One of the lotto games, Powerball games or something? Only the third time it's happened or something, but good
It
luck.
was $1 billion like a couple weeks ago, and then it's creeping up there now.
Okay.
So it's like in the 900 and something
Alright.
millions.
It's getting up there, isn't it? Yeah, well, good luck playing that, ladies and gentlemen. But you know, the old adage is if you don't play, you don't have a chance to win. But if I showed you your probability of winning, you probably wouldn't play anyway. So let's just drop the subject, move on. Okay, here we go. Now, to multiply two numbers in scientific notation, we multiply the numbers to the left of the powers of 10 and add the exponents of the tens. You may have to rewrite to put, now we might have to rewrite it or tweak it at the end so as to force it in the strict scientific notation form. I'll show you what that's all about in a moment here. All right, for instance, right here, if I was to do this problem here, okay, if I was to do like A here, 3 times 10 to the 5th power times 2.2 times 10 to the 3rd power, I'd multiply 3 times 2.2. And what does that give me? 3 times 2.2. 3 times 2.2.
6.6.
6.6 times, and now we're going to multiply the like bases of 10 together. 10 to the 5th power times 10 to the 3rd power. When we multiply like bases, we add the exponents. So this is going to be 10 to the 5 plus 3 power, or 10 to the 8th power. Question, is this product in scientific notation format?
No.
Now you're saying no, why not? Remember what scientific format was. To the left of the decimal point, we need an integer that is either a what? 1, 2, 3, 4, 5, 6, 7, 8, or 9. Do I have that satisfied? What do I got to the left of my decimal point? Do I got one of those integers? Son of a gun, it erased it. Okay. Anyways, what did I have? I had 6.6 times what? 10 to the 8th power. Do you agree? That's what I had. All right. Now, to the left of my decimal point, do I have an integer that's either a 1, a 2, a 3, a 4, a 5, a 6, a 7, or an 8 or 9?
So it is a scientific.
Yeah, it is. I got a 6 to the left of the decimal point. This is scientific notation form. We're good. We don't have to tweak this. All right, let's try the next one now. 5 times 10 to the 2nd power multiplied by 7 times 10 to the 3rd power. To do this, we take 5 times 7 first. And what's 5 times 7?
35.
35 times, now we multiply our like powers of 10. Like bases of 10 rather. 10 squared times 10 cubed gives me 10 to the what? 2 plus 3 power, or 10 to the 5th power. Again, when we multiply like bases, we keep the base the same and we add the exponents. So I have a question for you. Is this product in strict scientific notation form? Where's the decimal point on 35? I don't see it. Where is it understood to be? Where's my decimal point on 35?
So it'll be towards the left.
Well, it'd be just to the right of the what? 5, understood. Ladies and gentlemen, is this in scientific notation form? To the left of my decimal point, do I have an integer that's either a 1, 2, 3, 4, 5, 6, 7, 8, or 9?
It's
No.
No, I got 35, don't I?
Mm-hmm.
This is not scientific notation form. This one we have to tweak. Okay, we're not done with this problem yet. We have to force this into scientific notation form. But how do we do that?
Move the decimal over left and then add 1 to the exponent.
Yeah, all right. Nice job. Well, check this out. If you have a final answer that's not in scientific notation form after like performing operations on scientific notation numbers, I have a saying, ladies and gentlemen, it kind of goes like this. If we move our decimal to the left, we heft our exponent. If we move our decimal point to the right, we slight our exponent. I've been working on that for 20 some years. Let me write that down, show you what I just said here. If we move the decimal to the left, we heft. If we move the decimal to the right, we slide. It rhymes. If we move the decimal to the left, we heft. If we move the decimal to the right, we slide. Now, what does that mean? Because I have to move my decimal point one place to the left, we must heft up our exponent by 1. We must add 1 to our exponent. To heft something up means to build it up, okay? So if I move my decimal point one place to the left, I must heft up my exponent by 1. Final answer, 3.5 times 10 to the 6th power. That's now correct scientific notation format. And this is still equal to 35 times 10 to the 5th, though. Still equal. All right. So there you go, ladies. Just remember in the end that if you ever have to tweak your final answer after performing operations on scientific notation numbers, just remember the saying. To the left, we heft. To the right, we slide. If we move the decimal point to the left, we have to heft up our exponent by the number of places we moved our decimal point to the left. If we have to move our decimal point to the right, we have to slight our exponent or subtract off from our exponent the number of places we moved our decimal point to the right. So like if I had to move my decimal point, like say my decimal point was like in front of the 3 right here, then I have to move my decimal point one place to the right to put it in scientific notation form, which means I would have to subtract 1 from my exponent on 10 if I had to do that. Okay? So to the left we heft, to the right we slide. Now that only applies when we're trying to tweak a final answer to put it in the scientific notation form after performing operations on numbers. All right, and this is indicating our final answers here, of which I spoke of. Okay, there you go. All right, ladies and gentlemen, we're looking at classwork number. Which one is this? Anybody be keeping track? I know we did 1. This is 2, I think. All right, see if you can do these problems. See if you can, you can use a calculator to help you out. Multiply these scientific notation numbers together, but make sure your final answers are in strict scientific notation format. So you may have to tweak your answer based on what I just showed you. Okay, try these problems here. All right, let's take a look at the first one here. Okay. Now, 3.25 multiplied by 5.1. That's gonna give you 16.575. All right. Which we can see this is not in scientific notation form right off the bat here. Now, 10 to the negative fourth power times 10 to the negative 3 power is going to be 10 raised to the negative 4 plus negative 3 power, or 10 to the negative 7th power. So when you multiply like bases, you add the exponents. Now, to put this in scientific notation form, I'm going to have to move my decimal point between the 1 and the 6, which means I have to move it one place to the left. So to the left, we heft. So this is going to be 1.6575 times 10 to the what power? Now, to heft our exponent by 1, we add 1 to our exponent. So what's negative 7 plus 1?
Negative 6.
Negative 6 power. That's now in scientific notation form. Okay, so you have to do that little adjustment at the end. Let's try the next one here. 8.6 times 10 to the third times 9.7 times 10 to the negative 6. What's 8.6 times 9.7? We'll do that first. And 8.6 times 9.7 nets us 83.42. So that's 83.42. And this is going to be times 10 to the what power? 10 to the third times 10 to the negative 6. We add the exponents. 3 plus a negative 6 is negative 3. But this is not scientific notation form because the decimal point has to be between the 8 and the 3. So we're going to move it one place to the left to force it between the 8 and the 3, which means we moved it to the left. So we must heft our exponent by 1. So therefore, this is going to be 8.342 times 10 raised to the negative 3 plus 1 is negative 2 power. And there you go. Now that's proper scientific notation form. Okay. Are we getting this out there? All right. What if we had one like this? What if I had, hold on a second here. Well, let me think here. Hold on a second. Let me think. Well, let's just move on. We'll find one in our book. All right, suppose you want to divide numbers that are in scientific notation form. Okay. Well, what we're going to do is I'll demonstrate a couple of these here. Both these numbers are in scientific notation form. We want to divide. So what we're going to do is we're going to divide the 9 by the 3 times, and then we're going to divide the like bases of 10. So we'll have 10 to the 6th power, and that's going to be divided by 10 to the 4th power. So 9 divided by 3. 9 divided by 3 is what? 3. And Les Amis, when we divide like bases, what do we do with the exponents? Anybody? Do we add them? Do we multiply the exponents, or do we subtract them?
We add them.
No, that's when we multiply like bases. So if I had 10 to the 6th power times 10 to the 4th power, it would be 10 to the 6th plus 4, 10 to the 10th power. But we're dividing like bases. So what do we do with the exponents? We are to subtract them off. So it's going to be 10 to the 6 minus 4 power. That order of subtraction must be in that order. Numerator minus denominator. So therefore, this is going to be 3 times 10 to the what? 2nd power. Is my number in scientific format? Where's the decimal point on 3? I don't see the decimal point. Where's it understood to be?
In front of the 3?
Not in
Maybe
front of
behind the 3.
It just behind the 3. It's understood, just to the right of the 3. So is this number in scientific notation form? If the decimal point is,
Yes.
yes, it is. If my decimal point, if my decimal point is right here, Ladies and gentlemen, that is scientific notation form. Because again, the digit to the left of this point has to be either a 1, 2, 3, 4, 5, 6, 7, 8, or 9. It's a 3. That's scientific notation form. All right, how about this one here? So I'll tell you what, I want you to do these, ladies and gentlemen, this will be classwork. Just add it on to classwork 3. Just do these last problems here. I want you to perform the division the way I did above here. And make sure your final answer is in scientific notation format. Okay, go ahead. Try these last problems out, these last 2 problems. Classwork 3. Is my first answer in scientific notation form for B? Or need I tweak it? Is that scientific notation?
Yes.
Yes, it is. We're good. Anybody get that?
Yes.
All right, good. Second problem.
Where did the fuck my power come from?
Remember, when we divide like bases, we subtract exponents. Because you got 10 to the negative 5th divided by 10 to the negative 4th power, it's going to be 10 to the negative 5 subtract the negative 4 power. Careful of all these subtraction and minus signs here. All right, so therefore this is going to be 0.25 times 10 to the what power? What's negative 5 subtract the negative 4? That's really negative 5 plus 4, which is negative what, 1? Question, is this in scientific notation form?
No.
No, it is not. The decimal point, where do I have to put the decimal point for this to be in scientific scientific notation form here?
Right of the 2.
It's got to go just between the 2 and the 5. So to get it there, we got to move it one place to the right. Remember my saying? To the right, we slight. To the left, we heft. Since I moved my decimal point one place to the right, we have to slight our exponent by subtracting 1 from it. To slight it means to take away from it. To heft means to add to it. So this is going to be 2.5 times 10 to the what? -2 power. There's your final answer. That's now in correct scientific format, notation format. Anybody get that there?
Yep.
All right, see how we're doing this here? Okay. And this is all illustrated on the next page here. Of course, not in the detail that I have shown you. At least I don't think so. All right, well, pretty close. All right, can we apply scientific notation to the real world? You bet we can. Earth's orbit around the sun, ladies and gentlemen, is not a circular orbit. Our Earth goes around the sun, one whole trip around the sun in about 365 days. Did I get that right? 365 days? Isn't that 1 year?
Yeah, that's right.
But you know, the orbit of our Earth around the sun, ladies and gentlemen, is not a perfect circle. In fact, the orbit is kind of like an ellipse, an elliptical path. Here's the sun, and here's the Earth. Our Earth kind of goes around the sun in an elliptical path. This is kind of like a huge exaggeration of that, but nonetheless, it kind of goes around the sun this way. It's not really a circle, it's an elliptical path. Our Earth is actually closest to the sun. When do you think the Earth would be closest to the sun? January 3rd or July 3rd? Take your pick, ladies and gentlemen. What do you think?
July.
Wrong, but you're not alone. Just about everybody answers the way you answer, so don't feel bad. Ladies and gentlemen, ironically, the Earth is closest to the sun January 3rd. I think it's around January 3rd. That's called the perigee. The Earth is farthest from the sun around July 3rd. That's called the apogee. Why is it so hot in July then compared to January? What's the deal? You would think because the Earth is closest to the sun in January, it'd be hotter than July. What's going on? Anybody?
It's the tilt of the Earth's axis.
That's right. Yeah, it has everything to do with the tilt of our Earth on its axis relative to the sun, to the sun's rays. You see, in July, ladies and gentlemen, our Earth northern hemisphere is tilted towards the sun. Okay, so the rays strike the northern hemisphere almost at a perfect 90-degree angle, almost, not exactly. But in the wintertime, January, the northern hemisphere is tilted away from the sun. And so the rays strike the northern hemisphere at a very, very small angle relative to the surface of the Earth. It all has to do with the tilt of the Earth with respect to the rays of the sun, not really the proximity of the Earth, the distance from the Earth from the sun. That's interesting, but that's the way it works. What a paradox that is. How do we get on the subject? Oh, here we go. It's reasonably close to a circular orbit, but not exactly. It is a little bit elliptical. And my drawing was a huge exaggeration. It's not that elliptical according to my drawing. So, ladies and gentlemen, the radius is 9.3 times 10 to the 7th miles about. How far does the Earth travel in 1 year? The formula for the circumference of a circle is about 2 pi r. So I'll tell you what, I'm going to draw this again, but I need to draw it more like this in order to answer this question. They're saying the sun is kind of like in the center of our path around the sun, which is slightly elliptical, but maybe a little more circular than elliptical. Anyways, they say the radius of the sun and our Earth, here's our Earth way out here. By the way, the sun is a lot larger than the Earth. The sun could swallow up, I think it's thousands of our planets. That's how big the sun is. How come the sun looks so small then? Anybody? Why does the sun look so small?
It's like 1,000,000 miles away from Earth.
A little bit more than that. I think the sun is, how far away from the Earth is the sun? Is it about 93 million miles? I think it's about 93 million miles away from the Earth, about 93 million miles, give or take, according to, like I said. the closest approach of the Earth and the furthest approach of the Earth from the sun, January versus July. But generally speaking, it's about 93 million miles, give or take a couple miles. Anyways, ladies and gentlemen, they want to know the distance that our Earth travels around the sun in miles. What's the complete distance that it travels in making one circuit around the sun? Well, the circumference, or the distance, or the perimeter around a circle, is given to us by this formula: 2 times pi times the radius. They tell us the radius is about what? 9.3 times 10 to the 7 miles. Ladies and gentlemen, that's about 93 million miles. Our Earth is about 93 million miles away from the sun. And that's a good thing that it is. If we were any closer to the sun, we'd burn up. If we were any further away from the sun, we would be like Mars, where we'd be freezing like a popsicle all the time. Okay. All right. So, ladies and gentlemen, we plug in the radius, 9.3 times 10 to the 7th, in for the radius into the circumference formula. Pi, by the way, is an irrational number. Its decimal approximation is about 3.14. We will approximate this as 3.14. So you know what? This circumference, or distance the Earth makes around the sun, is going to be an approximation. Wavy equal signs, meaning it's not going to be exact because we approximated pi's value. In reality, pi's decimal rambles on forever and ever, never terminating or never repeating. A supercomputer in Japan took pi out to, I think, 20 trillion decimal places, and it still showed no signs of repeating or terminating. Safe to say it's probably irrational until that brilliant individual comes up in the future and says, ha, it finally terminates or finally repeats after the 20 trillionth and 1th decimal place. Smart aleck. Anyways, ladies and gentlemen, we multiply this by 9.3 times 10 to the 7th power. Yeah, it's safe to say pi is probably irrational. You got a calculator? Want to try this out? 2 times 3.14 times 9.3? Let's do that. What is 2 times 3.14 times 9.3? That gives me about 58. Okay, 58.404. And of course, this will be times 10 to the 7th power. Okay. That's the number of miles the Earth goes around the sun in 365 days. Is that in scientific notation form? The answer is what? No. We got to move this decimal point between the 5 and the 8. So to the left, we what? Heft our exponent. So one place to the left, we must add 1 to our exponent. So this is going to be 404 times 10 to the 8th miles is the distance the Earth goes around the sun in 365 days. That's the number of miles it goes around the sun. That's a lot of mileage. That's like, let's see here. If I was to move my decimal point to the right 2 places, I would slight my exponent by 2. So that'd be 584 what? Million? About 584 million miles the Earth goes around the sun. This distance, 584 million miles in 365 days. So I have a question for you, ladies and gentlemen. If the Earth goes around the sun 584 million miles in 365 days, how many miles per day is the Earth going around the sun? I'll tell you what. Take this 5.8404 times 10 to the 8th power, and let's divide that by 365 days. How would I do that on a calculator? How would I even do that? Well, hold on. I'm going to try to show you. I'll see if I can show you. I'd have to bring up my calculator here, though. I'm just curious. So I'm going to bring up my calculator. And I'm going to take 5.8404 times 10 to the 8th power. How would you enter that in on your calculator? Here's how you do that. You would say 5.8404. This would be the same way on the TI-830 too. Times 10 raised to the 8th power. Everybody see that there? You know, I really should have enclosed this number inside parentheses here, so I'm gonna put an open parenthesis. And then I'm gonna put a closed parenthesis at the end. And I'm gonna divide this by 365 days in a year. Wow. So there you go. So how do we even read this number here? Let's see, is that you know, we would read this: the Earth is moving at a speed of about 1,600,109 miles per every day. That's the speed with which our Earth is rotating or revolving around the sun. 1.6 million miles per day. Man, that's hauling, isn't it? You imagine getting your car and driving 1.6 million miles in one day. That is so not happening. Do you agree? Our Earth is really moving very quickly around the sun, but it just has a huge distance to cover. That's why it still takes 365 days to go around the sun one whole time. Isn't that amazing? All right. So we're done with that problem there. $584 million miles is the total distance around the Earth treks around the sun in 365 days about. Okay. All right, we're done with this PowerPoint here. Wait a minute. Oh, we did end it. What am I saying here? Okay, let's try to go have some fun, ladies and gentlemen, in our textbook. All right, so this is section 5.6. Now it's playtime. All right, let's go to our textbook, section 5.6, and see what kind of trouble we can get into. All right, let's see, 5.6, 5.6. Here we go. All right. And please do take the time out. Hopefully you have some time where you can maybe just at least look down through some of the examples that your author's laying out here. Hey, what's 9 to the 0th power? What's 9 raised to the 0th power? That's just 1?
One.
One.
Yeah.
That's just 1. Now, you don't have to read these sections verbatim, but, you know, it would be nice maybe just to look at some of the examples here. These are showing powers of 10 here. You can see the huge difference in magnitudes of these numbers here. 10 to the 0th power is 1. 10 to the 9th power is 1 billion. 10 to the 6th power is 1,000,000. 10 to the 3rd power is 1,000. In computer science, they call 1,000 a kilo, correct? Kilobytes means 1,000 bytes. A million, 10 to the 6th power is 1,000,000. They call that mega. That's the prefix in the metric system. That means million. Megabytes is 1,000,000 bytes of memory, let's say. 10 to the 9th power is billion. They call that giga. That's its prefix in the metric system. So gigabyte is 1 billion bytes. All right. 10 to the negative 1 power is 1/10. 10 to the negative 2 power is 1/100th. 10 to the negative 3 power is 1/1000th. Okay. 10 to the negative 4th power is 1/10,000th. 10 to the negative 6th power is 1,000,000th. And they use the prefix called micro. Okay, so microfarads might be the measure of a capacitor on a circuit board. Micro means 1/1,000,000th of a whole unit. So 1 microfarad would be 1/1,000,000th of a farad. Okay. And then you can go smaller and smaller and smaller and smaller and smaller. Let me show you something interesting here, ladies and gentlemen. What is the order of magnitude difference between 10 to the 9th power and 10 to the negative 8th power? Well, here's how you would figure it out. You would take 10 to the 9th power and you would divide it by 10 to the negative 8th power. And when we divide like bases, we subtract the exponents. So this is going to be 10 raised to the 9 minus what? Negative 8th power, which is really 10 to the 17th power. And so, ladies and gentlemen, we would say that there's the difference between 1 billion and 10 to the negative 8th power is 17 orders of magnitude larger. So 10 to the 9th power is 17 orders of magnitude larger than 10 to the negative 8th power. That's like comparing the size of the sun compared to maybe a grain of sand. Do you agree there's a difference in size there between a grain of sand and the size of our sun? Huge difference in orders of magnitudes here, all right? Humongous differences. All right, let's go on down, see what kind of fun we can have. Uh-huh. These are just simple evaluations here. What do you think -4 to the 0th power is going to be? -4 to the 0th power. -4 raised to the 0th power. What do you think?
1.
1. Hey, check this out, though. Is this saying the same thing? Is this saying the same thing as this right here? Careful. Here it's -4 to the 0th power, which is 1, but this is not saying -4 to the 0th power. This is saying the opposite of 4 to the 0th power. Well, what's 4 to the 0th power? 1, but what's the opposite of 1? -1. So this evaluates the -1. But when you put -4 inside the parentheses, 0 outside, that's just +1. Notice the difference there. Okay. All right, so just some practice here. 5 to the 3rd power times 5 to the 3rd power is going to be 5 to what power? What do we do with exponents when we multiply like bases? Add, subtract.
Add them together.
We add the exponents. So it's going to be 5 to the 6th power. 3 plus 3 is 6. What's 3 to the 4th power divided by 3 to the 2nd power? What do we do with the exponents? When you divide like bases, subtraction. This will be 3 to the 4 minus 2 power, which is going to be 3 squared or 3 raised to the 2nd power or 9. Okay. So notice there's a huge difference in these operations here, or these exponents. That's why you want to try to memorize those rules that we mentioned earlier. Number 27, what's 5 squared cubed? What's this equivalent to? 5 squared cubed. Do we add the exponents and call it 5 to the 5th? Do we subtract the exponents? 2 minus 3 is -1, 5 to the -1. Or do I multiply the exponents? What do you think? When you raise a power to a power, you multiply the exponents. It's going to be 5 to 2 times 3 power or 5 to 6 power. You are correct. All righty. So yeah, just, be familiar with those rules of exponents. In fact, be very familiar. I just memorize them. Especially if you're going onwards into mathematics, like I would memorize them. Oh, wow. Hey, look at number 43. All heck breaks loose. What's going on here? How would you simplify this expression? Anybody want to help us out here for number 43? What do you think you do first here to try to simplify this?
You cancel, cross cancel?
I mean, you could cancel, but let's not do that. That would be a mess. Let's not go there. We're not ready for that. Hey, how about the numerator? When I multiply these like bases, what am I going to do with the exponents?
Correct.
Add
No,
them together.
we're multiplying like bases, so we what? Add the exponents. What's 10 plus 12?
22.
22 power. And that's divided by 8 to the 8th power. Now, what am I to do with the exponents now that I'm dividing like bases?
Subtract.
We shift gears and use a different rule or property. We have to subtract the exponents. So this is going to walk out as being 8 to the what power? What was that?
14th.
14th power. Yep, 8 to the 14th. So this all simplifies down to 8 to the 14th power. Okay. All right. Maybe, well, help me out with this one, number 45. In fact, ladies and gentlemen, I'm going to have you do this for classwork. Number 45. I want you to simplify this expression. X to the -5 power times x to the 3rd power, all divided by x to the -9th power. This will really help you to run through your mind the properties of exponents. We'll call this classwork number 4. Number 45. Go ahead and simplify that expression. All right. Can somebody, or does somebody feel confident enough to kind of like walk us through this problem? Like, what did you do first? Anybody? Number 45.
I added the exponents together
So
first.
you multiply the x's together in the numerator. Okay, so x to the negative fifth times x to the third power. When we multiply like bases together, we keep the base the same and we add the exponents. So it's going to be x raised to the negative 5 plus 3 power. And of course, this sits over x to the negative 9th power. Now, what is negative 5 plus 3? Well, that's going to give us x to the negative 2 power. And then finally, to wrap this problem up, we have to divide this by x to the negative 9th power, in which case we must do what with exponents?
Subtract them.
Subtract them. What order? Does order matter? Our subtraction order?
That's the top has to go first and then the bottom.
That's right. We were taught with the rule we've seen to take the numerator power and subtract off the denominator power. Just be careful with all these signs here. It's like tap dancing on a minefield. We got to be careful here. Therefore, we got x raised to the negative 2. What's subtracting a negative 9? Same thing as adding a what? Positive
A
what?
positive 9.
And what's negative 2 plus 9?
7.
7.
Final answer should be x to the 7th power when all is said and done. Anybody get that?
Yeah,
Yeah.
I did.
Well, that's how we pursued that problem there. Okay. All right, let's see what else we got here. Write each number in scientific notation form. All right. Okay. Part of classwork number 4. Just add this right on the classwork 4. I want you to write these two numbers in scientific notation form. Go ahead. Those two numbers, 52 and 53. All right, first one here, we're going to move decimal point between those twos there. So how many places to get it there? Well, 1, 2, 3. Wait a minute here. Trying to write with the mouse. Let's see. So how many places we got to move it there to get it there? Let's see. So there's 1 place, 2 places, 3 places, 4 places, 5 places, 6 places. So it should be 2.22 times 10 to the 6th. Now this one, the second one, 53, the decimal point has to go between the 6 and the 1 to put this in the scientific notation form. So we got to move the decimal point 1, 2, 3, 4, 5, 6 places. So this is going to be 6.18 times 10 to the not positive 6, but 10 to the negative 6. That's a small number. That number is less than 1. Okay. All right. Any questions about that? We get them? All right. There's your answers. Well, the answer to that one there. So yeah, that would be your answers for those. Okay, now we're going backwards here. Let's see here. So see if you can do 62 and 63. We'll just add these right on. We got an open tab running on classwork 4. Just add those on to classwork 4. 62, 63. Write them back in decimal notation form. All right, the first number is a big number. The exponent on 10 is 5. The second number, number 63, is a small number because the exponent on 10 is negative 6. So to put number 62 is 7.72 times 10 to the 5th in the decimal notation form, you're going to have to move the decimal point 5 places to the right. And to put this small number, 3 times 10 to the negative 6 power and 63 back in decimal notation form, you got to move the decimal point 6 places to the left, with the understanding that the decimal point on 63 is just to the right of the 3, just to the right. When all is said and done, we should have these numbers in decimal notation form. Did anybody get these here? Are we looking at these here?
I got the
Yep.
second one right, but not the first.
All right. No, the first
Like
one.
I went the wrong way with the
Oh,
decimal.
wrong way. Okay. Yeah, positive exponents. The only way you're going to express this as a big number as it is you got to go to the right. If you go to the left, your number is going to get smaller and smaller and smaller. 0.07, 0.007, 0.00007. It gets smaller and smaller. So you got to go to the right. All right. So are we clear on how to go back and forth between scientific notation form and decimal notation form? Practice.
Yeah. Could we do could you do 65? I think I got it, but just
Yeah. All right. 65. Is this a large or small number, number 65?
small.
Small.
Small number. It's got a negative exponent on 10, negative 8, which means we have to move our decimal point 8 places to the left, not to the right, but to the left. Even despite it being a negative number out here, we don't care about that. We don't care if it's positive or negative out here. if the exponent's negative, we move decimal always to the left. If exponent's positive, we move it always to the right. So we got to go 8 to the left. So that's going to be one place to get it in front of the one. And then we're going to have to move it, what, 7 more places to the left, which means when all is said and done, you're going to have 7 zeros before you hit that 1. 1, 2, 3, 4, 5, 6, 7, and then you hit the 1, 4, 6. And there you go. That would be in decimal notation form there. All righty. That's a very small number. And like if you were to go back to number 62 here, if you had a negative in front of the 7 here, like you still move the decimal point 5 places to the right. This negative or positive out front doesn't change anything how we move our decimal point. So this would still be, it would be negative 7, 7, 2, 2, 3. It would be negative 772,000. Okay. So again, when your decimal point, when your exponent's positive, you move to the right. If your exponent's negative, you move to the left with the decimal point. This doesn't matter if you got a positive or a negative out front. It doesn't matter what's going on out there. All right. All right. Let's see here. Now we're going to start getting into some operations involving numbers in scientific notation form. And just remember, in the end, you may have to tweak your final answer. You may have to, move it to the left and heft, or you might have to move your decimal point to the right and slight your exponent. Okay, so just keep that in mind. All right, we'll have you do number 69. Throw that into the classwork 4. Go ahead and do that one, 69. Make sure your final answer is in scientific notation format. All right, now when you multiply 6.2 times 10 to the negative 2 times 4.3 times 10 to the negative 6, you're going to multiply 6.2 by 4.3 first. And 6.2 times 4.3 is 26.66 times, and then you're going to multiply your like bases of 10 together, 10 to the negative 2 power times 10 to the negative 6 power, which means when you multiply like bases together, you keep the base the same and you add the exponents. So this is going to be 10 to the negative 2 plus negative 6 power. All right, so therefore, when we do this, we're going to have 26.66 times 10 to the -2 minus plus a -6 is -8th power. But this is not scientific notation form. To put it in scientific notation form, the decimal point has to go between the 2 and the 6. So we have to move the decimal point one place to the left to get it over there, which means to the left we heft. So if I move my decimal point one place to the left, I must heft my exponent up by 1, add 1 to my exponent. Final answer then should be 2.666 times 10 to the -7th power. That's your final answer in scientific notation form. Did anybody get that there? All right, we could check our answer here and see if we got it right. Yeah, there it is. Oh, notice they rounded the last 6 up. Well, they rounded off to the hundredths place, 2.67. Notice that there, they rounded off to this place here. And since our digit to the right is 5 or larger than 5, we bumped the 6 up to a 7. And then we truncate the digits to the right thereof. So 2.67 times 10 to the -7. They didn't really say to round there. I don't understand what. Well, I don't know. Oh, it says rounding to how many decimal places? 2 decimal places. Rounding to 2 decimal places. See that in the instructions there? I sit corrected. And that's why they did round off to 2 decimal places here. 2.67. All right. Yeah, it's wise to read the instructions. Okay. All right, let's move on here. Okay. Now I want you to do problem number 77. 77, just throw that into the classwork 4 pot, okay? Divide those numbers in scientific notation form. Make sure your final answer is in scientific notation format. Number 77. All right, 4.2 divided by 7 is 0.6. And then 10 to the -2 power divided by 10 to the -3 power is 10 to the -2 subtract -3 power. Again, when we divide like bases, we subtract exponents. Well, this is going to give you 0.6 times 10 to the, now -2 subtract -3 is -2 plus 3. And -2 plus 3 is 1. So that's 0.6 times 10 to the first power. And now, ladies and gentlemen, we need to realize, though, that this is not in scientific notation form. we're gonna have to move our decimal point one place to the right to force this into scientific notation form. So that to the left of decimal point, we have, you know, an integer of 6. But remember my saying, to the right, we slight. So if I move my decimal point one place to the right, I must subtract off 1 from my exponent. And as it turns out, this is going to be 6 times, with the understanding that the decimal point is just to the right of the 6 now. Okay, 6 times 10 to the 0th power. But 10 to the 0th power is 1. So this is like 6 times 1, which is just what? 6. The answer is just 6. Or in strict scientific notation form, it would be technically 6 times 10 to the 0th power. I think they wanted you to leave it in scientific notation format. But yeah, that really would be equivalent to just 6 then. Okay. Anybody get that?
I did, but I left it to the 10 to the 0.
Okay, yeah, that's good. No, I wanted it that way. I don't think they wanted it as 6. They did want it as 6 times 10 to the 0th power. Well, and then they say it's also equal to 6. So either answer would be
Oh.
acceptable there. Either one's good. All right. Let's see what else we got here. All right, so we did all that, all this. All right, now they're going to give us some numbers here that are not in scientific notation form. They want us to write our numbers first in scientific notation form and then take care of the operation. All right, I want you to try 2 problems here, 2 last problems for your home classwork. Number 81 and number 83. First, you got to write your numbers in scientific notation form and then either multiply them together like in 81 or divide them in 83. Okay, so there's just one extra step to do these problems. Go ahead and do those. Number 81 and 83. Notice it says to round your final answer to 2 decimal places once it's in scientific notation format. All right, go ahead. All right, so the first one, 63 million, you want to write as 6.3 times 10 to the seventh first. 41 million, you want to write as 4.1 times 10 to the seventh, and then you multiply these numbers together in scientific notation form. 6.3 times 4.1 is 25.83. 10 to the seventh times 10 to the seventh is 10 to the 7 plus 7, or 10 to the 14th power. The problem is this number is not in scientific notation form. You have to move decimal point one place to the left. And because we move our decimal to the left, we must heft our exponent up by 1. So one place to the left, you must heft your exponent up by 1. Final, well, you would then have 2.583 times 10 to the 15th power. But they want your answer to be rounded off to 2 decimal places, which means we round off to the 8th place here, but we see a 3 to the right of the 8, and 3 is less than 5, so we keep the 8 as an 8, and we truncate or chop off the 3. So your final answer rounded to 2 decimal places would be 2.58 times 10 to the 15th. Anybody get that?
Yes.
Yes.
All right, last problem. 600 million divided by 25 million. First, you write 600 million as 6 times 10 to the 8th power. 25 million as 2.5 times 10 to the 7th. Then you divide 6 by 2.5, which gives you 2.40. And then 10 to the 8th divided by 10 to the 7th is 10 to the 8 minus 7 power, which is 10 to the 1st power. Notice we're lucky. This is already in scientific notation form. Technically, I think they wanted you to round to 2 decimal places. So since you had 2.4, I think you need to put the 0 to emphasize the fact that you really rounded off to 2 decimal places. Let's see if they did that with the answer here. They leave it as 2.4 times 10 to the 1st power. You know, they said in the instructions, they wanted your answer to round it off to 2 decimal places. Technically, ladies and gentlemen, if you're following the instructions to a T, you should have 2.40 times 10 to the 1st power. So I don't know, your author relaxed here a little bit, but anybody get either 2.4 times 10 to the 1st or this right here, 2.40 10 to the 1st. All right. So there you go. All right. And then there's just some application problems here. I'll give you some on Alex to play around with those. All right, ladies and gentlemen, I'll stay on the line for a couple minutes if you have any questions. If not, have a good day. We'll enjoy some of that sunshine and that warmth, which is obviously not going to last forever. All right, I'll be on the line for a couple minutes.
For 81, how did you get 7 for the powers? That's
Wait a minute. Which problem is that now?
81.
Oh, 81?
Yeah, were you counting the zeros or were you counting?
Yeah. Let's look at here. You see, you got to move your decimal point between the 6 and the 3 to put this in the scientific notation form. It has to go between the 6 and the 3. How many places is that? 1, 2, 3, 4, 5, 6, and then what? 7, correct?
Oh, okay.
6.3 times 10 to the 7th. So you can count
Okay.
the zeros. You can count the zeros. 1, 2, 3, 4, 5, 6. And then you got to count the 3 though, right? You got to move it one place
Yeah.
to the right. In between the 6 and the 3. So that's 7. All right.
Okay.
Okay.
Okay, now I got it.
All righty.
All right.